Hi, this is a spiral hook that I was taking from a 400 watt dough mixer, and this video I'm going to replace this aluminum with a 3D printed one, and I will test it by mixing it with the dough for 30 minutes to see if the 3D printed one can survive the breaking. And thank you for BIQU for sponsoring the filament for testing today, which is a carbon core 25 ABS filament. I think the first designer used clay for sculpting this hook because a lot of shape here is not created by using a CAD command, and there is no flat surface on here anywhere. If you look here, this protector is not flat. It has a curved and wavy surface, and also the top of the mounting hole is also not flat. Only one inorganic shape here that I can find is this hole and the key. As you know that the shape of the hook has to match the shape of the bowl. It's not interchangeable. So there's going to be a lot of steps to reverse this part because I'm reversing the sculpture, not a CAD model. When you move your thumbs on the flat face, I can feel the waviness of the surface. And the aluminum has the stiffness of 70 gigapascal, so it's very stiff. And the most stiff filament that I have is a PET CF. It has 4.5 gigapascal stiffness. If the hook is stiff, it can transfer the power from the motor directly into the dough more efficiently. But if it's flex or has low stiffness, it's gonna lose the power. You probably need more time to mix the dough if the hook is not stiff enough. 3D scanner that I'm going to use this video is the Creality Sermoon S1. In my previous video, I was mentioned about the frame limit of this Sermoon S1, and I have information from the Creality that the new update in September will resolve the issue with the frame limit. So they are going to extend the frame limit so that you can scan longer, and also they will resolve the issue with the color texture scanning in the blue laser mode. Okay, this is how I will scan this hook. First, I want to capture inside of the hole and the keys, also the opening slots here. I will handheld this part, and then I will use a single line laser to scan inside of the hole and also the pocket. And after that, I'm going to put this on a turntable and scan the rest of the hook. I have already installed 6mm markers around the holes area. 7 markers here is enough for the scanner to track. I won't be using the global marker because I'm going to handheld it, and after that I'm going to put it on the turntable with a lot of markers, so I cannot use the global marker. And I will be using the resolution of 0.2mm. I scan it with a single line. Let me check. And next I'm going to delete my hands. Okay, next I'm going to click on continue scanning. And I'm going to switch to parallel lines. So next I'm going to switch to single lines. Okay, let me make a new scan. I need to flip this because I have already completed the scanning inside of the hole, so I don't have to scan the hole again. Okay, next I'm going to fill supply cloud 0.2, remove the markers. Okay, here's the result. Let me turn off scan number 2. Let's check the first scan that we scan the hole. It's all complete. Okay, let's merge it together. Process, alignment, automatic alignment. Okay, now it's merged. There's some noise here, so I want to delete it. Let's turn on here. Okay, so it's much better. Okay, next I'm going to export the point cloud. You can export the point cloud one by one. Click on here, export model. Okay, and if you want to mesh it, 0.8 million. Mesh will eliminate boundary between two scans, so it looks cleaner than the point cloud, but it has some processing that it will change the dimension. I won't be using the mesh for reverse engineering. The dimension will change, so I will use the point cloud. So inside the hole is complete. There's no opening. Okay, let's see what is going to happen if you just drop the 3D scan files directly into a slicer. Since you have a complete scan without any blind spot, why can't you just print it directly? Let me show you. And then I'm going to slice it. Okay, here's the problem. Problem number 1. Because the guard, the circular guard here is not flat. Nothing is flat here. Scout by hand. So when you make a 3D scan, it's going to capture that uneven surface as well. And unflatness is larger than 0.2 millimeter. It's going to show in a step of the layer height, and it's going to look really bad. That's number 1. Number 2, you can't split this circular guard. It has a lot of support, see here, and you're gonna need a lot of time to remove it. You should be splitting this part, print it separately, and then glue it back on. So you can't do this without reversing in CAD. That's number 2. Number 3 is the hole diameter. So when you print the hole parallel to your print bed, this one is 12 millimeter. It's going to be smaller when you print this, so it's a chance that you cannot fit, or the fitting will be too tight if you just print this directly. Okay, this is what you get when you do direct printing from the 3D scan. Uneven surface is more than 0.2 millimeter. Then when you print it, it's going to create a step like this. And also in the back side here, this hole is 12 millimeter. So when you print with the FDM printer, when the hole is parallel to your print bed, the hole size will be smaller than it is. So it will be difficult for fitting. You need to force to make it fit. It's quite difficult to remove. Okay, this is car compare. I'm going to drop in hook number 1 and hook number 2. Next I'm going to merge this to point cloud together. The point cloud is merged. I'm going to change the color, something bright color, choosing 3 points. to be flat. Move it to the origin point. See, so now it's moved to the origin point. Now you can clearly see the inside. So we have a nice clean cross section. Cross section in the hole. Alright, next I'm going to export this to Autodesk Inventor by converting this into ABS files format. And then I'm going to use the recap to convert it to RCP files. And then I'm going to import it into Autodesk Inventor. Okay, this is the model that I have reversed in Autodesk Inventor. I split the model into two parts, a circular guard and the hook, because it's easier to print the circular guard separately, and then I will glue it back together after printing. And this is the point cloud from the 3D scan that I use for reference. Next, I'm going to show you step by step what does it take to model this part. And I use only three functions: extrude, loft, and sweep. So this is only three functions that I use to model this part. Okay, first I create a circular sketch here, diameter 26mm, a little bit larger than the original part because the original part is not circle. If you look here, it's not circle. You can see here because this is not a mill part. They sculpt it by hand. And next I extrude it for 15mm. I also use a taper because the original part has some taper applied to it. Okay, next I make a second sketch, just big enough to support the base of the hook. And then I extrude it for about 3mm. Draw another sketch here on the top. Then I extrude it with the taper 4 degrees. Another sketch, just a simple circle. I extrude it with a taper. This one is higher than the original part. I explain later why I do this. Okay, next I create a hole. This hole is larger than the point cloud. As you can see, this point cloud, the hole is larger because when you print it, you're going to need some clear lens. So I put a 0.2mm clear lens. So after printing, it's going to fit perfectly. I end the hole with a cone shape. This will help eliminate the support. This is why I need to extend the height of this cylinder. Okay, next I'm going to create a cutout for the key. I use the point cloud as a reference. So if you can't scan inside of the key, you can see this wall. And you can use it for the reference. And if your 3D scanner cannot get into the inside of the key here, you're gonna need to use some sort of a measurement to get this alignment. Create another sketch here, another extrude cut, and then I use fillet command to match the profile from the point cloud. Create another sketch here, and then I extrude cut for the second key. Okay, make one chamfer here. Another chamfer here, and I add 2 fillets on 2 corners. Okay, next I'm going to create the first profiles of the hook. I use a slot command to create a capsule shape, and I extrude it toward the main part with some taper, 7 degrees taper, and I keep extruding until it reaches the bottom part. Okay, next I create a second sketch. It's the same shape, slot shapes, but it's a little bit shorter. And I loft it using loft command. Okay, here's a profile for the second loft. Just tracing the sketch, nothing difficult. And I also use 3 spines to create a rail. The siding will follow the shape of the point cloud. I use 3 splines to control it, and I can use this. I can move this, adjust this later. Okay, this will be the second loft. Okay, this will be my third loft. Sketch for the third loft, and this is a spline that I will use to control the rails. This is the third loft. Okay, I create a sketch for the fourth loft. The profiles of the hook change all the way through here. Okay, this will be the rail that I use. Okay, and then I loft it. This is a fourth loft command. And next to this, this hook has a constant profiles from this point to this point. So I will use sweep command. It will be faster than loft. If you have a constant profile, use the sweep command. So I create this 3D lines. It's a spline with 4 control points. So I adjust the shape of the spline to match the point cloud, and I will use this face for the sweeping profiles. Now I sweep it. From this point, the profile shape will change smaller, and it's gradually change the shape until here. So I need to use the loft command again. Okay, here's the rail, and then I loft it. Another loft with 3 rails. Another loft also with the 3 rails. This sketch has ellipse shapes. It's not circle, it's ellipse. I loft it with 2 rails. Now it has constant profiles from this point to this point. So I will use sweep command using this line for the rails. Okay, this is sweep command. It's faster than loft. Okay, another loft because the profiles has changed. Another loft with 3 rails. This will be the final loft. Small profiles here. So this is the end of the hook. All done. I decided to add some strength to the 3D printed part by adding the thickness of this support plate here. So now it's about 6 mm in total. And then I extend the edge here for 3 mm for supporting the circular guard. Because I'm going to put a circular guard over this, I need some area for applying adhesive. Next, I create a sketch for the circular part. This is a different part. I leave a gap for 0.2 mm, so it won't be a tight fit. Tight fit is 0.1. If it's 0.2, it's a loose fitting. So now it's all done. The designing of the hook using the point cloud as a reference. The entire process, I don't use any vernier caliper because when you do a reverse engineering, you need to trust your device. You can't use multiple tools for measuring because it's going to give you a discrepancy. Let's do some stress analysis. So I apply a pin support here, frictionless here, and this is a contact point. So I apply frictionless and another frictionless here. On this face, I apply force for 5 kilograms, 50 Newton. I think the force that I apply when I make a circular movement in the mixing bowl is 5 kilograms. I don't really have this data, so I have to estimate it. And here's the result. So if I apply 5 kilograms on this end here of the hook, it's going to create 32 megapascal wall misses stress on these 2 points. So this is the point that it will likely to break. If it will break, 32 megapascal is the tensile strength of most common ABS filament. So if the BIQU filament provided me for testing today has a tensile strength of 65, so it should be able to pass the test here. So let's find out if this simulation is correct and if it is going to break. But from this simulation, it should survive if the provided tensile strength is correct. If I scroll it down, okay, you can see if you do this in CAD, you are going to have a super flat face on the first layer, and circle is circle. So the result will be much different than the direct printing from the 3D scan data. Okay, we have a problem here. As you can see, this part here is print isolated in an island. So, and it will take a very long time to reach the main part, and I think it's going to fall down this part with this small of the support. So I need to paint the support. You need to paint the support here so that it will help provide enough contact area so it won't be falling. Okay, now this is much better. So I never used the BIQU filament before, and they have a very high carbon fiber content. It says right here, carbon core 25. They have a carbon fiber mixture of 25%. It looks different from the carbon fiber filament that I have seen before. From the outside, it looks just like an ABS filament, I can't see any carbon fiber texture on the outside of the filament. This is because they have 2 layers. They put the carbon fiber into the core of the filament. I'm not sure if you can see this, but I can't. It's in the core, the fibers, and the fiber strand is quite long, 0.5 millimeter. That's what they put in the specification. Most ABS filament will have tensile strength about 30 megapascal, but in the website, BIQU ABS CF has tensile strength of 65 megapascal. Usually, the non-carbon fiber filament will have stiffness, Young modulus, about 2 gigapascal, but with the carbon fiber filament like this one, PETCF, this one has 10% carbon fiber content and the stiffness is 4.5 gigapascal. But BIQU doesn't put this physical property in their website, so I don't know what is stiffness value of this filament, but from what I can see is that the filament is soft, much softer than the 10% carbon fiber filament here, and they look quite different from the outside. See, this is a regular carbon fiber filament. It will have a matte surface from the carbon fiber, and this one is look just like an ABS filament because they put carbon fiber inside of the core. Only one property that's improvement from the non-carbon fiber ABS is the tensile strength, and for the stiffness I really don't know if it has any improvement in that department. So in this test, this spiral hook will be a good testing scenario for this filament. Okay, here's a texture from the print bed, and this is top layer. I think it's a little bit stiffer than ABS. And it's not too difficult to remove. And the support is quite easy to remove. I've already mixed some flour with the water. Okay, next one is the PETCF from Kexel. It looks very carbon fibers, and the surface is rougher than the ABS CF from BIQU. Okay, let's test this one. Aluminum 115 grams, ABS carbon fiber, BIQU 40 grams, about 3 times lighter than the aluminum, PETCF 52 grams. So PETCF is 30% heavier than the ABS CF. If I flex it, this thin plate, I can feel that this has a lot more flex than the PETCF. Yes, this one is stiffer, even though it has 10% carbon fiber content. So I think that we are getting close for replacing the aluminum part with the 3D print engineering plastic. There's going to be a better filament coming out, and sooner than later it's going to be able to entirely replace the aluminum casting, 3 times lighter, similar tensile strength. What they have to improve is the stiffness. Now it's 12 times lower than the aluminum. So if they can increase the stiffness, so it's coming close. Okay, thanks you guys for watching. See you again in the next video.